Hi everyone, welcome to day 2 of Starlight. Today I'm going to be doing the first talk, and this is going to be a survey talk where I'm going to be discussing some recent advances in zero-knowledge proofs. So SNARKs and zero-knowledge proofs are something which have been around since the 80s. But I would say they only really became practically efficient enough to be using in real-world systems with Pinocchio. And this happened in 2013. Basically, they were relying on different assumptions. They put a lot of the work into a pre-processing phase. So they would do a lot of the work before the system went live, which meant that they didn't have to do the work again once it was live. And the result of this was that when Zcash came along and with the application of anonymous transactions, trying to make sure that everybody could keep their identity secret while doing these cryptocurrency transfers, they had a system they could rely on in order to actually make that a real thing. So it's been 5 years since this happened, and since then, our knowledge about zero-knowledge has been moving really, really fast, because everybody's now very interested. We're seeing that this is a real thing. We can really use it. We can have these awesome applications. And this has just given motivation for lots of researchers to look into it, lots of implementers to look into it, and just really make sure that we're doing everything we possibly can. So in this talk, I'm going to be focusing mostly on the past 2 years. So we're not going very far back at all. I might add in the odd paper or two, which is like further back, but generally speaking, I'm going to be trying to keep it super up to date and modern. So as researchers and actually as implementers as well, there's a number of challenges and questions that you might be thinking about when you're trying to use zero-knowledge. Obviously, the most important one is, are we actually working with schemes which are secure? Related, but I'd say maybe a bit less important is what happens if our security assumptions get broken. I mean, obviously it's important, but it's maybe less likely than we come up with something which is fundamentally broken. Then we might be thinking about, okay, well, we can handle Merkle trees, we can handle anonymous transactions. What about if we want to handle something more complicated? What if we have a very, very large system and we want to be able to prove that? Can we do this? Can we make implementation easier? Certainly when Zcash first launched, everyone was having to use the libsnark library, and this was not the easiest thing. And I'd say we've moved on quite a way since then. Obviously, efficiency. Efficiency is always, if you can be more efficient, you can do more stuff, it's always good. And then there's also the question of how do we decide which protocols we do and which protocols we do not want to use. The latter question is possibly more of a standards question than a research question, because as a researcher, you're always going to say, you should use my scheme. You just are. But when it comes to standards, that would be the whole community getting together and looking at the protocols and saying, okay, these ones actually do work for these purposes and these ones work for these purposes. So I've tried to remove as much jargon as I can from this presentation. Probably I'm still putting in too much. I'm always putting in too much, but there are 3 sort of buzzwords which are going to be coming up a fair amount. So I just want to mention what they are to anyone that doesn't know first, such that you can hopefully still follow. And this is about different types of setup which you might be using when you're generating your zero-knowledge proof. So there are essentially 3 types of setup: trusted setup, universal setup, transparent setup. When a scheme is, when you're talking about which scheme you use, you would have to choose between one of these 3. And the trusted setup is probably the most difficult to actually instantiate. It comes with the most challenges for practitioners, certainly. Because what this means is that your scheme is only secure, you only get soundness if before you start and go live with your system, you have a group of n parties who jointly generate some parameters which are then used whenever you generate a proof. And the challenging thing here is that these parameters are very specific to the application that you have in mind. So if you want to do upgrades, if you maybe come across some bugs and you want to fix them, you would have to run the whole setup again, which means finding sort of, let's say, 200 people again to actually take part, to actually verify that they've taken part, maybe post a thing on Twitter saying, I took part. You'd then have to get people actually then verifying the transcript, making sure you've done everything properly again, just all of the work that you've done in the first initial setup phase would have to be redone. This is a problem that goes away completely if you have a transparent setup. If you have a transparent setup, then this initial phase where you have a group of n parties jointly generating parameters just doesn't exist. You can generate the parameters just from hashing, just from saying, here's, I don't know, a picture of the sky. I'm going to apply a hash function. At the end of it, I get some parameters. They look random, and that's enough for me to generate zero-knowledge proofs. The sort of in-between phase between these things is a universal setup. And here again, you are going to have that, we call it a multi-party computation or a trusted setup. That is going to happen. But once you've done it, you can use that same setup across multiple different applications. So this, for example, would mean that with the Zcash setup, that could be reused by other companies if they have a different application in mind. It could also be reused by Zcash if they happen to find a way in which maybe they can prove something a little bit faster and they want to have that improvement. Or even if they want to switch to a different universal setup proving scheme for that matter. Currently, Zcash is running on Grot16, which has a fully trusted setup. The main purpose of the Orchard upgrade, I believe, is to try and move to a transparent setup in order to remove that layer of trust. So now we sort of have different types of setup, and we're sort of saying the schemes we have, is it even possible to get them faster? Can we do even better than we're currently doing? My intuition for this is that if we're using a trusted setup, proof of time, maybe there's improvements that can be made. But for the proof size and the verifier time, it seems quite unlikely. There has even been lower bounds sort of saying that Grot16 is as low as you can possibly go, only through group elements, that's perfect. Recently, there has been a work that says, actually, that's not quite true. If you allow for a scheme which isn't perfectly complete, so just very occasionally a prover might not convince a verifier, then you can actually do it with 2 proof elements. But if we're talking 3 group elements, 2 group elements, this is not something which I can really imagine going below, because that is almost the size of your security parameter, really. When it comes to transparent setups and universal setups, however, the picture looks quite different because the tools that we have to use are smaller. And so it is possible that we might be able to make improvements. And it's also possible that we can't. We haven't really had many results either way. For schemes with a universal setup, there's been 3 big works in the Sonic was not in the past 2 years. Marlin and Planck were just about, which have been improving on the state of the art. So the idea behind all of these schemes is that when we take our problem, the thing we're wanting to prove, be it an anonymous transaction or something else, we're going to represent that using something called KCG polynomial commitments. KCG polynomial commitments have quite a special property of having very small I have written opening time, I meant opening proof size, and verifier costs. So if we're wanting to create something with small proof sizes, they are ideal. And the other nice thing about them is that if you can represent your scheme purely using polynomial commitments, then polynomial commitments don't actually say anything about the form of the circuit. They are an object in themselves. They know nothing about what you're trying to prove. So it creates a way in order to make things actually universal. So not dependent on your circuits, they can be reused across different applications. The proof size and the verifier costs are mostly determined by the number of commitments that you have to send and the number of commitments which you have to open. And it is possible that maybe we could send less commitments and maybe we could open less commitments in order to get those proof sizes down a little bit. One thing which I have personally tried to do in order to improve efficiency in this line and completely failed at is currently with universal setup, we have these constant proof sizes, but actually all of the schemes we have with constant proof sizes have quasi-linear prover time, so n log n. And this is due to the fact that they use fast Fourier transforms, more or less. We also do, in the literature, know of schemes which have linear prover time, so just n. They don't use any fast Fourier transforms, but logarithmic proof size. Having a linear prover is really quite nice, not only because it means that your prover is smaller once you start talking larger statements, but also if you want to parallelize your prover, so run it over lots of different machines, then this becomes much easier to do. Basically because fast Fourier transforms are not that easy to parallelize. It's possible, but it's a bit of a challenge. So we have systems which have logarithmic proof size, linear prover. We don't have systems which have the best of both. So we don't have anything which has a linear prover and a constant proof size. And I don't know whether this is fundamental or not. All I'm really saying here is that I've tried and I've not succeeded. When it comes to transparent setups, people have been using some fairly different techniques. One quite fun technique that people have been looking into is class groups. So these are an alternative assumption, essentially trying to mimic the RSA assumption about having groups of unknown order. But RSA has a trusted setup because we don't know how to generate RSA parameters without using multi-party computation, whereas class groups don't. Class groups you can generate just from public parameters. However, they have been about for a long time, but they haven't been very well studied in most of that time until now, when people have found important applications for them, not only including SNARKs. The bigger one is probably verifiable delay functions. So we know they exist, but we possibly need a little bit more research and people are researching this currently at the moment, and just making sure that the way that we're instantiating them is, actually hard to attack. The proof sizes are bigger than universal SNARKs. So we're talking in the paper, which is where I got the numbers from, they were saying that it cost them 8.6 kilobytes for 2 to the 20 constraints. Whereas when we're talking universal SNARKs, I believe it's currently about 500 bytes. It's certainly less than a kilobyte though. So there is a concrete difference in proof size. Another protocol which has been looking at what we can do with a transparent setup is Spartan. This is working in discrete log groups, and they have square root proof sizes and square root verifier work. Actually, this work is something which you can scale, so you can make the proof size smaller and the verifier time bigger, or the proof size bigger and the verifier time smaller. But if you want to but I think square root is a good way to get in your mind sort of what the trade-offs are there. And these are built off entirely standard assumptions. More recently, again, we have seen a work called Dory, which is basically able to do a polynomial commitment scheme in bilinear groups, which have logarithmic proof sizes and logarithmic verifiers. Using this polynomial commitment scheme, Sethi and Lee were able to generate some zero-knowledge proofs which have transparent setup, standard assumptions, logarithmic sized verifiers, and in general, when it comes to the asymptotics are ticking all the boxes for things we know how to do. Again, though, we're talking a bigger proof size. So looking at their paper, I didn't compute this myself. It was saying 39 kilobytes for 2 to the 20 constraints. And I think most of that cost comes from the fact that the proofs which they're sending are target group elements, not source group elements. And what that essentially means is that these are 6 times as big. And if you're multiplying all of your costs by 6, things do grow a little bit. The third one, obviously, which we have already heard about it at this conference already, so I'm probably not going to fill my entire presentation talking about it, although I think it's really cool, to be clear, is Halo and Halo 2, which also have a transparent setup. And these have been specifically designed for recursion. They should be efficient for any verifier where the problem that you're trying to prove is larger than the recursion threshold, so how efficient it is to actually represent the verifier. And again, it relies on standard assumptions. Moving on to a slightly different train of thought. When it comes to how certain we are of security, designing and implementing zero-knowledge arguments correctly is something that we really, really want to get right. If we don't, then we could find ourselves, before I continue, there's a question. What's the state of the art on compressing target group elements? So I know that we can represent them using 6 times the size of one G1 element. I can't remember the citation for that. I've never heard of a work which is able to compress them further. If we could compress them further, then it would directly improve the efficiency of quarks by that same amount. Going back to the security question, yeah, mistakes can cost very large amounts of money, obviously. But the even harder thing about this space in particular is that we do want zero knowledge. We want it to be the case that even though a number of trusted parties, say, generated these trusted parameters, which then everyone is using to generate the zero knowledge proofs, even those people should not be able to tell one honest party from another honest party. Nobody can do that. So this means that if you can't tell an honest party from another honest party, it also can be quite hard to tell an honest party from an attacker that's managed to forge a proof. Because if the proof looks identical to your normal proof and then you're not actually linking it to anything public such that someone can sort of go up to it and say, this person stole from me, it can be very difficult to even know that you're being attacked. So from this point of view, designing systems such that we know we are being attacked, of course, is better if we're able to do that. But if we're not, then just making sure that we audit things as thoroughly as we possibly can and put as much attention into getting things right is arguably just as important as efficiency, if not more so. So researchers have been looking at this, and they've been looking fairly closely at the security arguments in particular, and sort of saying, how can we accurately portray the real implementations in some kind of model where we can reason about these things and make sure that there's no trivial attacks, at least, without sacrificing any efficiency. The one model which has proven really successful at doing this is the algebraic group model. And this is an idealized model which is capable of proving many, many fast schemes, including Grot16, including Sonic, including Plonk, including Marlin, including Halo 2. Most fast schemes that I'm aware of that are actually being used in practice, the actual proof is in the algebraic group model. So it's very friendly towards making sure that you can get the security proof correct. The general idea behind it is that an attacker can only generate a proof if they also know how they generated this proof. So then you get a representation and you can say, using this representation, if they cheat, then I can break this hard problem. In Marlin, we use the algebraic group model in order to prove many different versions of the KCG polynomial commitment scheme. And as mentioned before, this is very useful for building SNARKs that have universal setups. If we wanted to not use the AGM and instead use a knowledge assumption, then we would end up with something which is twice as large. So when it comes to KCG, you sort of, the original paper, when you first look at it, it looks very much like you're not going to need to rely on the algebraic group model, and you might be able to use something perhaps more standard, such as the non-programmable random oracle model. That's one we'd really like to be able to prove this in. I did try. So in particular, I looked at the strong correctness proof in Appendix C.4. But from what I understood, and maybe someone understands this better than me, that proof is actually inherently using the fact that the adversary does know a representation of the polynomial. So they're sort of still relying on the algebraic group model, if only implicitly. So if we could find a way in order to prove that in a normal model, it wouldn't improve efficiency. It would only be a sort of, it's fun that we could do this, but it would be fun if we could do it. The algebraic group model has also been used to prove non-interactive inner product arguments secure. So non-interactive inner product arguments, the first thing that you should think of when you hear this is bulletproofs. And these are something which people often use for proving range proofs, for example. The original arguments which were presented, they have correct security proofs, but the security proofs are in the interactive model, which is assuming that there is a prover and there is a verifier and they're talking to each other, going back and forth, going to and fro, and at the end of it, the verifier is convinced that the prover hasn't cheated. In order to make it non-interactive, which is what we actually need when we're trying to use it in order to get public verifiability, for example, such that anyone can look at this proof and be there like, oh yes, that's correct. Typically what we would do is we would apply the Fiat-Shamir transformation and just hash all of the verifier, all of the proofs messages in order to get the verifier challenges. However, from a theoretical standpoint, actually applying the Fiat-Shamir heuristic in the algebraic, in the standard model, and the oracle model, is not that simple in this setting. And what actually happens if you try and do it in a naive way is you end up with an extractor, which is not polynomial time. Hence why we actually need to do this proof in the algebraic group model. A third scheme, which is proven secure in the algebraic group model, is GROT16. And actually, we've also improved the security proof in the sense that we're able to prove that GROT16, as implemented in Zcash with this trusted setup ceremony, shouldn't have any naive attacks. So if the algebraic group model is sound and the Q discrete log assumption holds, then even if you have an update ceremony, there are no attacks on GROT16. When we're sort of thinking, okay, is this an okay model? We're proving everything that we're using in this model. Is it good? But something which is fairly reassuring is that we do actually know that it does exist in the standard model, but this is assuming IO, which is a fairly strong assumption. As in, like, if you wanted to instantiate it with IO holding, you'd be talking large groups than the ones we're currently using, but still, they exist. We don't know any of any attacks on the model itself, which is also quite nice. Well, it's also extremely important. If we knew of any attacks, then we obviously would not be able to use it. And this includes an additional 10 years, possibly more than that, years of the generic group model being a thing before people even got to attacking the algebraic group model, where people have not been able to find anything substantial which would imply that it's not okay. Can I define IO? I'm not going to try and define IO, sorry. Okay, so this gives us some confidence in the model. On the other hand, as someone that has been actively working with this model a lot in my research, I do think we could do better. So the main aim of a security reduction in the AGM is not necessarily to be pretty, it's not necessarily to be a work of art, it's just to increase security that the scheme that you're using is correct. The problem with AGM reductions in sort of more complicated systems, for example, when we do Grok16 and we also add on a setup phase, is that the reductions start to get very, very involved. You end up with every variable that ever appears in the system needing to be actively kept track of and sort of included in this large matrix expression, which you then have to argue about. And this sort of means that from a human perspective, the chances of me getting something wrong or someone else getting something wrong, or an auditor looking at the work and not picking up on the fact that something's wrong, is higher. Like, the simpler we can get our security reduction, the easier it is to check. These reductions are not simple. One solution to this, of course, would be automated proof checking software, and I think that would be a wonderful thing. Currently, there is some software which can be helpful for proving things in the generic group model, which I think would probably suffice for our purposes, but actually it doesn't work for SNARKs. The reason being that the win condition isn't that well defined. What you're saying is, if I am able to produce a verifying proof, then someone else is able to extract my witness, and therefore I must have known the witness in the first place. This is not the same as saying, if I'm able to generate a proof, then I can directly break an assumption. So actually trying to convert that in a way that you can then reason about in proof checking software is something which I think we could do, but that hasn't been done. So if we found a way to improve how we do this, either on paper or using software, or a combination of the two, then I think that would be quite a useful contribution. The KCG Polynomial commitment schemes, which I've been talking about, since people have connected them as being very important for generating universal SNARKs, there's also been some work in trying to make them more efficient. And one really nice result, which came out recently, that hasn't been formally written up in any kind of paper or security conference, is that it's actually possible to open n proofs, so generate n opening proofs, independent opening proofs, at the same time, in time n times log n. And I provided a link for the PDF explaining how to do that on the slides. This actually has some implications, by the way, for the original VSS scheme presented in the original KCG paper, because what it means is that their prover time for generating those opening proofs would be n log n rather than n squared, which makes it much more possible. Another improvement which has been made is that a single KCG style proof is actually sufficient for showing that the same polynomial opens to many different points, and you can at the same time. So if you're just talking to one verifier and you want to convince them that all of your openings are correct, you only need to send one proof. You don't need to send a different proof for every opening. When we're trying to find research papers which are useful, interesting, novel, fun, one of the really good ways to find these is to look through the some popular cryptographic conferences where most sort of serious researchers would be trying very hard to get their work published. The top conferences, in some of the top conferences for more theoretical purposes would be crypto, Eurocrypt, AsiaCrypt, and TCC. Security conferences tend to be more practical. This would be more thinking, do you have an implementation? Do you have a use case? Is it something which we'd want to use in real world systems? And here the big three would be security and privacy, CCS and Usenix. And generally for a more crypto themed paper, I would expect that CCS would be the more common one to send your paper to. When I'm saying this, I should probably stress that when we say peer review with these conferences, this is not the same as saying that these works that appear in these venues are ready for production. It means that somebody on the committee has looked at it and gone, this is interesting, it excites me, I want to hear more about it. Yes, we should audit it. Yes, other people should read this. It's not saying that they've come through it with like a well sharpened pencil or something and just made sure everything's correct. It's unfortunately not quite as strong as that. There's also a fair number of people that don't like how conferences are run at the moment, that would like to see something which accepts more papers maybe, or which is accepts more papers is the most common one I've heard actually, because they don't like sort of the same paper going for review over and over and over again, with it being perfectly fine, but just a review or two saying, I don't like it. This is something which I think is actually quite a valid concern. I would kind of warn these people when they're saying this, that deciding which papers to read and which papers not to read is a very political process. Every researcher is going to be saying, read my paper, it's the best thing ever. And when you're coming in as an outsider, if you don't have these conferences to look at, then you kind of have to take people's word for it, and you'll probably go to more well-known authors, or you'll go to people that you've heard of. So if there is a really good result, which has maybe come from someone that is less well-known, it becomes much harder for that to become noticed. And I'm not saying that this means we should stick with conferences as they currently are. But I do think that acknowledging the very political side of things, if you're trying to design a new system, is important. It's a personal opinion, obviously. Okay, one area which has been making huge progress in recent years is trying to prove something, statements which are even more complex than what we can currently do. So maybe we're even talking billions of constraints. And when we're talking billions of constraints, it becomes quite likely that Grot16 is not going to be your best option. One option that you do have is to switch to schemes which rely on more symmetric primitives. And the reason for doing this is because symmetric primitives are more efficient than public key primitives from a computation point of view. Downside is that you do end up with large proofs, and you do end up with longer verifiers. Another thing which these types of protocols need to consider if they're talking this many constraints is that memory actually does become a factor. If you're only talking 2 to the 20 constraints, you're not going to run out of memory on your scheme, you don't care. But if you're talking billions of constraints, then it's very likely that you will run out of memory on your machine. So you need to find a way in order to generate the proof where the prover doesn't necessarily store the whole state at the same time. Another technique which is quite good for handling very large circuits is garbled circuits, and these typically rely on oblivious transfer. These are especially good for systems which are naturally represented by Boolean circuits, so circuits with just zeros and ones and logical operators. And this would often be true, for example, if you're proving lots and lots of statements about symmetric key primitives. But if we are talking what can we do with public key primitives, then the answer is quite a lot. Because even though the statement might be very, very large, if what we're proving is actually just the same problem being proven over and over and over and over and over and over again, then we can start to use recursion. And it's basically what this would do is every time that you generate a proof, you prove that, for example, your state transition from the previous state is correct, and also the proof of the previous state transition verifies. This means that you can sort of start with an initial state and just do a state transition, prove it's correct, do another state transition, prove it's correct, and prove the previous proof was correct, do another one, prove it's correct, and prove that proof of the previous one was correct. So at each point in time, you're only actually proving a fairly small thing. You're updating your proofs incrementally. So this can help us handle very large statements, such as, for example, the full size of a blockchain. If we want to formalize this in what does this mean in other systems rather than just for pledges and commitments, one formalization which has come up recently, which seems to work, is a split accumulation scheme. And this covers the idea that you can have efficient accumulation even if you don't have an efficient verifier, as long as your batched verification time essentially is fast. Proving more complex systems. Okay, so I'm still talking here about what if we're proving the same thing over and over and over and over again. If we just want to prove the same thing over and over again, we might be able to use just a single layer of recursion if it's not something which is being updated incrementally, but if it's something that we can do all at once in a one-shot fashion. And in particular, we can aggregate Grok16 proofs really, really fast, because we don't need to represent the Grok16 verifier as an arithmetic circuit. We don't need to compress it down to MP. Instead, we can work more naturally with the algebraic structure of Grok16 proofs in order to come up with a prover which, yeah, is algebraic, and so concretely very fast. And this approach is something that is actually efficient enough to be used for Filecoin's proof of space application. So the paper on the screen here is where they talk about how they were actually able to implement this and get it working for their particular application. What happened here actually is they came up to us and they said, on your previous paper, you've been talking about how to aggregate Grok16 proofs, but actually you need a different trusted setup, and we can't run a different trusted setup. We've already run the trusted setup for Grok16, and just doing it again is going to make it not worth our while. So the point of this work was to say, okay, you don't actually need to do a different Grok16 setup. You can work with the same Grok16 setup as long as you have two of them. If you have two setups, then that should be enough in order to be able to run this aggregation, as long as those two setups are on the same curve. Recursion can also work for post-quantum systems. So Fractal does this. It uses a SNARK built from Reed-Solomon codes in order to apply recursion in order to be able to prove very large statements in a sort of updatable manner. Here you're going to end up with larger proof sizes, but you don't have any public key operations, which can make things a bit faster, a bit easier to run. Another type of large statement which people are often looking to prove would be machine computations. So these are so if you have a highly complex statement, then you might not want to represent it as a circuit. You might instead want to represent it as something that looks a little bit more like C code, with jumps and with additions, and just with a set of operations which you're trying to apply one at a time. If you're wanting to prove a machine computation, then at each step, what you're going to need to do is prove that the computation has been carried out correctly. And then you're going to have to prove that all memory accesses that are made over the course of the execution are consistent with each other and with the execution. What it allows you to do is to split the problem into lots of smaller problems, which reduces the memory requirements on the prover. And this is exactly what plookup does. The plookup is a very promising technique when it comes to proving Ethereum virtual machine transitions. There's a good chance that this might work. It's also the use case they bring up in the paper, which is fairly exciting, is that you can efficiently batch many range proofs at the same time using this proving system. And that means that if you have lots and lots of zeros and ones in your circuits, essentially from all of the range proofs where you're trying to show that you don't like overload the field, this becomes something which is efficient to run for the prover. Likewise, there have been works which have been discussing can we parallelize machine computations, and they've had some fairly useful results there. Okay, I'm at my 5-minute warning, so I'm going to be flicking through the last slides a bit quicker. The final topic which I will be discussing really is about lattice assumptions, which are an alternative assumption which could be useful if, for example, the discrete logarithm problem gets broken for quantum reasons or for other reasons. One other nice thing about them is that they have very useful homomorphic properties. So unlike Algebraic, encryptions can be added, and you can add lots of them, and then you can decrypt at the end and be able to compute the sum of the added encryptions. So if we're wanting to prove something about the encryptions that we've added in this homomorphic way, we might want to work with an assumption which is more natural to the scheme that we're using, the encryption scheme. We might not want to use something which is discrete log based and doesn't look at all like the assumptions we're using. And for example, it would be using different fields. Implementation work is lagging behind a bit, and this might be because NIST hasn't quite finished standardizing them. They're very, very close, and it should be within the year that that's done. So hopefully once they do, implementation should become a lot faster. I'm actually, I think, going to skip this slide more or less, more than just sort of saying lattices aren't automatically quantum secure. Because they're in the random oracle model, and the random oracle does weird things when you start introducing quantum. Being able to handle weird things that happen when you start introducing quantum is something which, from this year's crypto agenda, looks like it's might be a solved problem, but the work isn't out yet. They claim to be able to instantiate HTML in a way that only costs 2 to 3 times HTML. I have a few implementation pieces of improvements, which I sort of think the world should know about. So I'm going to briefly mention them again. The first is BlastPy International, and this is a very fast library for generating multi-exponentiations, which are usually the bottleneck in discrete log-based or pairing-based SNARKs. So if you use BLAST, it should take off a chunk of that computation. The other one is ArcWorks, which is a library written in Rust, which aims to be both fast enough in order to give you a good feel for what numbers are, even be used in practice, but is also very user-friendly and should be something which, you know, most developers should be able to use. I mean, I managed to use it, so if I manage to use it, it is doable. When it comes to actually writing the circuits, which is the hardest part, 2 of the big ones which people are using at the moment are Circon, where you write the constraints directly, and Socrates, which is a more user-friendly option if you maybe don't feel up to writing the constraints directly. Also, if all you're worried about is writing a ZAP or application on zero-knowledge application on Ethereum, which uses zero-knowledge proofs, but you don't want to get into the details of how they work, then this is a project that EY have been working on called Starlight, which might be able to help you with that. Okay, thank you very much.